Everybody's okay? Let's continue our session. So it's our pleasure to invite Nikonow to take his talk about magnetite and Bushveld Complex. Thank you.
Yes, thank you and good afternoon. I think we have a nice continuation of the talk we just had before, but now just with a bit more focus on the analytics. I will talk about micro energy dispersive X-ray fluorescence and laser-induced breakdown spectroscopy applied to the titanium magnetites of the upper zone of the Bushveld Complex. So I was in a project funded by the German Research Foundation, DFG, called 2D/3D Fusion. It works on the upper zone of the Bushveld project, and we had some cores donated by Impala Platinum for academic research, which were donated in the framework of the ICDP Bushveld Complex drilling program. And at first, I want to acknowledge Professor Rolfse and also Ilja Wexler for helping us getting our hands on those samples. So the two aims in this project were to develop a drill core scanning method based on hyperspectral imaging, laser-induced breakdown spectroscopy, and spatially resolved energy dispersive X-ray fluorescence spectroscopy. That was the first aim. And the second aim is to examine those monomineralic layers in order to get insights on the processes which took place to form those. And we have three sample layers, including the adjacent material from one drill core BH7772, in total 14 meters. To give you an idea of what we sampled, the red boxes are the samples that we have. The black is the magnetite. We have one sample from layer 21, one from layer 17 at 248 meters, and another about 25 meters above the main magnetite layer, which is here at 1039 meters. But I will mostly focus on this one here, on the layer 17 at 248 meters. So to give you an idea of what the samples look like, first of all, we thought magnetite should be massive magnetite, but as you can see here, there's a lot going on and there could be many students analyzing the structures and much more that we have here. But I will focus on this area here at 248 meters. So to give you a quick overview on the methods that we use, we have talked about already today about the micro uEDXRF. We use the Tornado Plus from Bruker. We can map element distributions from carbon to uranium at a resolution going down to 20 micrometers, but here in this case we used 40 micrometers. And one advantage of this method is that we can automate almost everything. So we can put in the samples and do it on Friday, and on Monday we have measured all the samples. And by now we have 2 of these devices because they run almost 24/7. So we have here our sample, one example. With our Tornado, we get the element distribution, but what we really want to have is the mineral distribution here. And for that, we use an in-house software tool called Petrographic Analyst, which allows us to automate all the processing of the data, also the mineral classification. It is a bit like ChemScan or MLA, but just for this different device. Also, a big part of my work was to develop a mineral database where we store spectra of more than 8,000 mineral samples from the Bushveld Complex, including, of course, solid solution series of plagioclase, pyroxenes, and so on. And also we have additional information in that database from microprobe analysis, such as anortite number, Mg number, and also titanium, chromium, vanadium content in the magnetite. And the aim is, among others, to get the modal mineralogy, as you can see here. With a mineral classification, you can count the pixels and get the modal mineralogy. Then another method that we used was laser-induced breakdown spectroscopy. We also get element distribution maps, but for all elements. And the advantage is that we don't need any sample preparation. We have a focus of maybe 1 centimeter, so you can put in the drill course and just start the measurement. And we go down in the spatial resolution to about 75 micrometers. So this is the overview of one of the drill cores that we have. This red box shows our sample. You can see here in dark the magnetite, and here those brighter areas are the plagioclase-rich areas. So this is a section from the drill core. It's a bit small, so I rotated it. And so you can see here in blue, the bluish colors are plagioclase. Gray is the magnetite with some amount of titanium. And you can see here several layers or lenses of plagioclase. Here also some sulfides, and here again we have the contact zone to the anorthosite and the gabbronorite here. So this is what was said already. We have a gradual top contact and a quite sharp but irregular footwall contact. Now, this is the mineral classification, and in our software we have the possibility to visualize also more than just minerals. I said before we have, for example, the titanium content, and now I plotted only magnetite, but I colored, the colors represent titanium concentrations within the magnetite, and you can see here it's mostly somewhere around 12 or 13%. So generally in this section it's quite constant. We have some boundary effect, I will not talk about that. And if we look on the general distribution of titanium, from our samples, we have those 3 sections at 223 meters. I didn't show that here, but we have there about 16% of titanium. In this sample here at 248 meters, we have 12%. And at 1039 meters, we have less than 10% of titanium. So there is an upward titanium increase. Now we took thin sections from our samples and compared the micro uEDXRF data from here to the electron microprobe data, and we can see here that it is actually quite similar. We have for this 223 meters, which we said was 16. The median is also about just below 17. For this sample here, we have about 14 or 13% of titanium, and this one has the lowest. So you can see it's not a replacement of microprobe, but you get a good idea of how the concentrations are. Now, the same can be done with the chromium distribution, and this is again just magnetite colored according to the chromium concentration. And you can see here the almost black is very low concentrations, and the green colors or bluish colors are around 1%. And what you can see here probably is, or maybe I give some help, there is at the bottom a very dark color, then we have bluish and greenish colors, then it's going up towards darker colors again, and then we have these, so there are several cycles of that upward depletion of chromium. But this is a bit complex. So I looked into the literature, and I think many of you know this. There is, this is the chromium content upward depletion. Every time the feldspar comes in, there is something happening. Here you can see this was 10 centimeter sampling distance. We have here 5 centimeter sampling distance, and you can see that there's something like an increase or a reversal. Then we have a more recent paper with 2 centimeter sampling distance, and you can see here there's a reversal where the anthracite comes in. So from 2 centimeter sampling distance, we went to 75 micrometer sampling distance with the LIBS scanner. We measured a stripe of 1 centimeter. And this is the data. This is what I actually want to show and explain. First of all, I will mention that the procedure is from Meima et al. So on the left side, you see the LIBS chromium intensity. This is relative values. And I masked all minerals except magnetite. And I masked also magnetite with some silicon, calcium, titanium, and so on, because we can have mixed pixels. So I wanted to have the pure magnetite. And this is what is plotted here along this drill core. Now, what can we observe here? There's a general, not so clear upward depletion of chromium in the massive magnetite, which is here the gray part, the massive magnetite. This general trend is interrupted by several reversals near the anaphysitic layers. Here in blue, blue is plagioclase, and you can see it here going up, going down. So at the bottom contact of the plagioclase, we see this increase of chromium going up here, going down here. Then the plagioclase comes in again. It goes up and then down. There we have again a plagioclase layer and so on. So this is what we can observe. There's also some scattering in the disseminated magnetite. This might be due to still some left mixed pixels with low chromium in the plagioclase, of course, but it's also known from the literature that the disseminated magnetite is more variable in concentration than the magnetite. But it is actually far more complex than it has been described before in the literature, and we think this is due to the new opportunities having really high resolution here. So I said before, these were just relative values from the LIBS. And to validate what we measure with the LIBS, because LIBS is quite fast and you can measure without a lot of preparation, we took thin sections. So these boxes here in the different blue colors are thin sections. This is the mineral classification here. So we have 5 thin sections from these different areas. And now this is the microprobe analysis coming. So this light blue is this thin section. And here we have the microprobe data. The x-axis is the chromium, and the y-axis is actually the y-axis here from the drill core. And what you can see here, we see the large scattering as well in the microprobe data. Here in the second part, we see this drop in the LIBS data as well as in the microprobe data. The next part is here. We can see again this nice drop in the chromium concentrations. And I think which is most visible or remarkable is this large drop here, where the plagioclase comes in. There is a large drop from about 1.5% of chromium going down to less than 0.5%. In the last one, there was so little chromium and almost no pure pixels. So we had no LIBS data, but you can see the trend already. There's almost no chromium inside this thin section magnetite. So to conclude, the LIBS data provides relatively clear chromium trends on a micrometer scale. The data is comparable to electron microprobe data, and we can do all of this without preparation of thin sections and even for full drill cores. So I'm almost out of time. You can do the same With vanadium, it's the same process, so I can skip this, and you probably know the literature as well. Just to give you a quick overview of what happens with vanadium, this is the same, just vanadium now. And you can see in the massive magnetite layer, the trend is less pronounced. And what is astonishing, there's a general trend of upward enrichment, which is contradictory to the overall trend in the upper zone. And in the disseminated magnetite, we can see there is a large scattering, and there is also a clear higher vanadium concentration compared to the massive magnetite. So to conclude here, we can say that the microXRF provides a quick overview on chemical and also textual information for full drill cores. The information is available at high resolution, speaking of tens of micrometers, and even without thin section preparation. And the continuous measurements with tens of micrometer resolution reveal small scale variations, which we could confirm with the electron microprobe on thin sections. And also the microXRF and the LIBS seem for us as suitable tools to visualize minor and trace element trends on a micrometer scale, which helps to select samples for further detailed analysis a lot, because we have a lot of samples and this is really helpful. And we also think the method combination is a helpful tool for this kind of research where spatial relations of the minerals play a role. And also we think that these methods are the missing link between field observations and the micro observations from microprobe or so. So thank you for your attention.
We have time for a couple of questions. And how long it takes to measure?
It depends. If we use, for example, 20 micrometers resolution for a thin section, it takes about 3 hours for the microXRF.
Okay.
So after 3 hours, you have the measurement of the thin section. It's just 4 centimeters by 1.5 centimeters.
Okay, thank you very much. One question.
Yeah, very interesting. So I don't know if I might have zoned out somewhere in there, but I presume like from the textual information you've got there, you could do crystal size distribution information, grain alignment,
yes,
groupings. If you can do dihedral angles, we could just chuck our microscopes away.
I think this is an ideal
potentially very powerful
to check the 2D information that we have there.
Yeah.
Yeah.
Thank you.
So our next speaker is Karina, sorry.
No problem.